So here we're going to talk about the Bohr model of the atom. Now the Bohr model of the atom, shown here, has one proton, and our one electron can be in any number of possible n states. So it can be in the n equal 1 state, or the n equal 2 state, or 3, or 4, or 5. And there's actually an infinite number of n states. I've only shown the sort of first 4, but you can see very clearly that as I go higher and higher in n states, the n states get closer and closer and closer together. Those n states represent places where the electron could be. It's either in the n equal 1 state or the n equal 2 state. The electron can't be in any sort of intermediate. So we have, in the case of hydrogen, the electron in its lowest allowed energy state is called the ground state for the electron. And in the case of hydrogen, the ground state for that electron in hydrogen is the n equal 1 state, sort of the lowest it can sort of be. Any other higher state where the electron is sort of hanging out is called an excited state. So in the case of hydrogen, an excited state is the n equal 2, n equal 3, or n equal 4 state. This allows us to then talk about the energy difference between the different energy states. So here is the equation, sometimes this is referred to as the Rydberg equation. Gives us the relationship, the change in energy, if you will, from an electron going from some initial state to some final state. So delta E, final minus initial, is equal to this constant, 2.18 times 10 to the minus 18 joules. And there's a negative sign in there, times this ratio, 1 divided by nf squared minus 1 divided by ni squared, where ni is the initial n level and nf is the final n level. Now this equation has a sign convention, meaning that the sign of delta E tells you which direction it's going. The electron is either going from a lower energy state to an excited state, or going from a higher excited state to a lower energy state, whether it be the ground state or some lower excited state. And we can, this equation is relatively straightforward. We'll go through a couple examples here in a moment. Relatively straightforward in terms of doing the calculation. But again, there's a sign convention that if NF is less than Ni, meaning we're going from a higher energy state to a lower energy state, the sign of delta E will actually be negative, which confirms with our sign convention from our other equations. So that means our energy is, our photon has a certain energy and the energy is given off. Just to sort of emphasize this energy difference, here is a picture, and this is actually to scale, that shows you the energy spacings between the various n levels. So as you see, the difference in energy between the n equal 1 state and the n equal 2 state is by far the greatest of any of the energy levels. 2 and 3 are closer, 3 and 4 are even closer, and then as we get closer and closer to infinity, they get they start getting really, really close. And actually it turns out if I take a hydrogen that's in its ground state, so the electron in the n equal 1 state, and I put in 2.18 times 10 to the minus 18 joules, that will actually take the electron up to the n equal infinity state. What does that really mean? Well, these energy levels, these n energy levels, the value for n sort of tells you the size and energy of the orbital, where that electron is. And if I put in that amount of energy, I'm essentially putting it in the n equal infinity state. And if it's in n equal infinity, what that basically means is that electron has gone so far away that it's no longer being influenced by that one single proton. And we can almost think of it as an ionized hydrogen atom. So now we can do a relatively straightforward calculation using the Rydberg equation, calculating the energy, wavelength, and frequency of a photon of light. It comes from a hydrogen atom whose electron is going from the n equal 5 state to the n equal 2 state. So our Rydberg equation, again, is very simple. There's our NF, where it's going, and our NI, where it's coming from. So in this case, NI is 5 and NF is 2. So drop those into our equation. That ratio, the difference is 0.21. So we multiply that by 2.18 times 10 to the minus 18. We get a delta E of 4.575 times 10 to the minus 19. Now, as you can see again, our delta E is negative, and that's a sign convention that tells us that the energy is, that a photon is being given off. Now, the equation in this equation, which tells us how energy is related to the frequency, this has no sign convention. All these numbers have to be positive because we're talking about the energy coming from a photon. We can't have a negative frequency. So when we plug in our energy in this equation and put it into this equation, we have to change the sign and make it positive because everything in this equation must always be positive. And that's just sign convention, and the rules of sign convention are we can change the sign when we need to, depending on the equation. So we drop in our energy, which is in joules, divided by Planck's constant, 6.626 times 10 to the minus 34 joule seconds. And we get a frequency of 6.906 times 10 to the 14 reciprocal seconds. Calculating the the wavelength is relatively straightforward. From here, we know that frequency times the wavelength is equal to the speed of light, which is 3.0 times 10 to the 8 meters per second. We take our speed of light, divided by our frequency, seconds cancel out, and we are left with a wavelength of 4.34 times 10 to the minus 7 meters. Now I should make one quick mention as to what things are required for you to memorize and what things you don't need to memorize. On exams or quizzes, you will always be given most constants, so you will never have to memorize what the speed of light is. I'll always tell you what that is. You'll never have to memorize what Planck's constant is. I'll always give you what that is. And you don't have to memorize large equations. So the Rydberg equation, there's no need for you to memorize that. If you ever are doing a quiz or anything and you need these things, I will give them to you. When you're doing homework problems, you might have to look them up, look in your notes, but that's the nature of homework problems. I do expect you to memorize simple equations, and the two simple equations on this screen that you are responsible for is this equation and this equation. Those two things you do have to memorize. So now we can do sort of like the opposite calculation. Given a photon with a wavelength of 103 nanometers, nanometers is, n is a metric prefix for 1 times 10 to the minus 9, which is not a number I would expect you to memorize, so I'm giving it to you. And we know NF is 1, and we're calculating n sub I. So the first thing we have to do is calculate what that energy of that photon is. We have the relationship between frequency and Planck's constant and energy. We also have the relationship between C and wavelength. So we can combine those two equations and come up with that delta E is Planck's constant times the speed of light divided by wavelength. So we know the wavelength is 103 times 10 to the minus 9 meters, which is the same as 1.03 times 10 to the minus 7. We're just moving the decimal place over 2 to make it scientific notation. And we calculate a delta E of 1.93 times 10 to the minus 18, but notice I changed the sign. Planck's constant is positive, C is positive, wavelength is positive. All of these numbers are always positive, but yet I have a negative delta E. Because the equation we're about to use, the Rydberg equation, has a sign convention, and if it's an emission, which we're told it is, going down to the NF equal 1, the sign of delta E must be negative. So we're going to go and just change the sign, make it negative, because we can do that. So now we drop it into our Rydberg equation. We know NF is 1. The only thing that's left here is n sub I, which is what we solved for. So a little bit of algebra, which of course you're responsible to be able to do this kind of algebra. Solve for Ni squared is 9.09, which is close to 9. Now, the reason why I'm going to get away with doing that is because I know that the n's must be integer values. I must have an n either 5 or 4 or 3 or 2 or 9 or 156, but it can't be 2.5 or 3.5 or 3.02, 3.03, or whatever you get when you actually take the square root of 9.09. It has to be an integer value. So we're gunning for an integer value, so we got to, a value of 3.02 is essentially the same as 3. So our answer is 3, not 3.02 or whatever this would come out. The reason why it's not exactly 3 is because we are told it's 103 nanometers, and there's a little bit of an error bar in that. If we were to carry that out to 6, 7 significant figures, then we would be obviously much closer to 9. But close enough for what we're trying to figure out.